turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to this week's Naked Scientists podcast, the show that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith. Coming up, samples back from space reveal tantalising insights into where the life-linked chemicals that kick-started biology on Earth could have come from. Also, the impact of China's DeepSeek AI model on society, finance and the global tech market, and why imported olive trees turn out to be the perfect cover for stowaway snakes and insects.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
Up first this week, 5 years ago, a NASA spacecraft successfully collected samples from the nearby asteroid Bennu, which is about 40 million miles away. The samples were successfully returned to Earth in September 2023 and shared among various labs internationally who have expertise in analysis of material like this. The first batch of results have now begun to trickle out and have been published this week in the journal Nature. And they lend weight to an interesting hypothesis that asteroids like Bennu might have been producing some of the exotic chemicals that helped to kickstart life on Earth. Sarah Russell at London's Natural History Museum leads one of the research teams, and she spoke to us from NASA's press conference on Bennu this week.
At the Natural History Museum, we have a great collection of meteorites, so we have some expertise in looking at asteroids, which is what most meteorites are fragments of. So we got an allocation of this material and we've been analysing it for the last year or so.
What does it actually look like? When it turned up before you began analysing it, what does asteroid dust look like?
Well, this asteroid is very dark. What we got looked like about a teaspoonful of black sugar, if you can imagine that. So it's that sort of grain size, but completely black.
Is it black because it's been hit by sunlight, or is it naturally like that? Has anyone scratched below the surface so you know roughly what you're analysing?
Yeah, absolutely. We've basically done everything to it, including cutting it in half, the bits in half. And yes, it's black all the way through, mostly, except there are some patches of white, which is part of the interesting part of what we're talking about today.
So apart from looking at it visually and chopping up the grains, how have you actually analysed it then?
So we've done this whole suite of analyses on it. So for each individual grain, we CT scanned it. So just as when you go to hospital, you might get a CT scan, which shows what your insides look like. We did the same thing on these grains to see what they look like on the inside. And then we put them in an electron microscope to look at them in much greater detail. And we also looked at their chemistry, what elements they were made of.
Wow. So come on then, put us out of our misery. What is the bottom line?
The rock is mostly made of a clay mineral, which traps a lot of water, so it's very water rich. And we were kind of expecting that because that's what it looked like from space. But what we weren't expecting was that it also contains little crystals of salt. And that was completely unexpected to us. And we think that these probably formed in little underground pods in the asteroid of this briny, salty fluid that then started to evaporate away and leave the sequence of salts. And we see similar kind of sequences on Earth, on lakes that have dried up, can leave these layers of salty material on them. So we've been comparing them to terrestrial salts. But also we think that this might happen quite a lot over the solar system. So we see similar salts in moons of Saturn, like Enceladus, also on Ceres, which is the biggest asteroid in the asteroid belt. And so we wonder if these salts are actually telling us something pretty universal about what happens to rocks in space.
How would it have been in a salty environment then, this body that's now an asteroid?
So we think that Bennu's parent body probably formed in the outermost reaches of the solar system. There it's very, very cold and icy, so it would have accreted ice and rock. And then the ice started to melt, and then this water interacted with the rock and produced both the clays, but then there was obviously some left over that made these pods that became salty because they had the ions from the rock added into them.
When you say it melted, would that be when it came closer in to the solar system? What would have melted it?
Yeah, no, it was probably melted very, very early in its history because when it first formed, it would have been very slightly radioactive. And so the radioactive heat could have melted the water.
Ah, right. Okay. So how did it end up in its
Yeah.
present position then if it formed way out yonder in the solar system?
Chris, that's one of the big questions that we're trying to understand how things moved across the solar system from the outermost part to the inner part. So it might have been in the early solar system, Saturn and Jupiter were not in the stable place they are today. They might have been moving inwards and outwards in their distance to the sun, and that might have disrupted these bodies and forced them to hop into the innermost part of the solar system.
Apart from the saltiness, are there any other interesting chemicals in there that make us kind of go, that is interesting?
We also have an organics team, and so they've been looking at all the carbon-based molecules, and they found there's this huge zoo of different complicated organic molecules. So these aren't things that were formed by life, but they are molecules that may potentially be the ingredients for life. They found things like amino acids and nuclear bases, which are molecules that make up part of the DNA of living things. So what we think is, firstly, these briny fluids might have actually helped make these organic compounds. So they might have been a really great place for these organic stuff to get cooked up and be built. But then also, if asteroids like Bennu were around in the early solar system, which they certainly were, and they impacted the Earth, they would have seeded the Earth with both the organic molecules, plus also water, plus also essential nutrients from the salts like phosphorus and sulfur that life needs to flourish.
Do you think then, or would a model then be that in the early solar system, we've got lots of raw materials floating around? Some of it accretes into bodies like Bennu, which just also happen to be radioactive, so they've got their own inbuilt cooker. And that provides the conditions, together with some of that water, to cook up, as you put it, some exciting chemistry, which then through gravity is dumped onto nascent planets like the early Earth.
Yes, you've exactly got it. And I don't think this would have been an unusual asteroid. So if an asteroid formed early in the solar system, it would have been slightly radioactive. And it's very likely to have had these very common elements of carbon and hydrogen and so on that make up these organic materials and water and salts as well. So I see this as probably being a widespread process across the solar system. It is inevitable that asteroids like this would have rained down on the early Earth and would have made it a lot more conducive to life.
And they would have rained down on a lot of other bodies as well, presumably. So therefore, they were giving everywhere an equal opportunity.
Yes, absolutely. If this model is right, then absolutely it should be quite a widespread process. So why not have life everywhere in the solar system that has enough heat to support it? And of course, also in early Mars as well. So Mars is a bit cold now, but it would have been much more habitable in the early solar system. So there's no reason why life couldn't have started there as well.
Isn't that amazing? Sarah Russell there, and that study has just come out in the journal Nature. The emergence of a Chinese-made artificial intelligence model called DeepSeek has shaken the tech industry and global markets, as well as bruising the egos of those in Silicon Valley and the White House. Even US President Donald Trump got in on the action.
The release of DeepSeek AI from a Chinese company should be a wake-up call for our industries that we need to be laser focused on competing to win, because we have the greatest scientists in the world. Even Chinese leadership told me that.
Donald Trump on the announcement this week of the Chinese DeepSeek AI platform, which has shaken Silicon Valley and knocked billions off the share prices of some of the world's leading tech giants. But what exactly is DeepSeek, and why has it unsettled tech innovators and investors to such an extent? Here's Mike Wooldridge, who's Professor of Computer Science at the University of Oxford, where he specialises in artificial intelligence.
DeepSeek is an example of what's called a large language model. And large language models are the AI programs that have taken the world by storm over the last few years. So the most famous of these is ChatGPT. And they're very, very large scale, very general artificial intelligence systems. And they were surprisingly powerful, which is why ChatGPT got so much attention when it was released. They were unexpectedly powerful. But their capability came at a cost. They're extraordinarily expensive to develop and require really hard to imagine computational resources to build. So we don't have precise figures, but a GPT class model to build would require something like 20 to 40,000 AI supercomputers running for months. And the cost of that runs into hundreds of millions of dollars. What that meant is that the number of organizations with those resources at hand to be able to do that is very, very small. It's basically the Silicon Valley giants and a very small number of state level actors. Now, DeepSeek come along, they announce a model which seems to be as capable as the current crop of large language models. It seems to be up there with the best of them. And yet the claim was that it was built for a tiny fraction of the cost of those models, which means that the advantage that Silicon Valley had and what's called the moat, the thing which kept everybody else out of this market, looked like it might be evaporating. And that panicked Silicon Valley.
Do their claims stack up? Not just in terms of performance, but their claim that they can do this so cheaply. Do you think that that was a bit of fanfare to get them traction, or is it the reality?
They have, it seems, done it comparatively cheaply, but not so cheaply that we're all going to be building large language models in the shed at the end of our garden. They've told us that they used a network of a couple of thousand of GPUs, so much smaller than the kind of scale of supercomputers that we use to build ChatGPT and the like. But if you dig into the statistics, they required 3 million hours of processing. So AI supercomputer, a GPU running for 3 million hours. Now you can only do that if you have thousands of those running in parallel. Now the cost of their cluster, I did some back of an envelope calculations. It looks like something like $50 to $60 million to buy those GPUs. And 3 million GPU hours at $2 an hour, the running cost of those amounts to $6 million. So that's where they get that headline figure on. But still, that scale means, for example, my research group has one GPU and my students fight over getting access to it. There's no way we could do that. There's no way we could replicate that. So they haven't exactly given this technology to the masses, but nevertheless, it looks like it's a real advance.
There were claims made, though, that this was being done using lower grade chips than the industry class. And that's always been a sort of political thing, hasn't it? Because China has, and some other actors have been prevented from having access to the sorts of technology that would enable them to make these very high-end computer chips. So they're using lower grade architectures. Is that the case, or have they just sneakily got hold of what the world thought they didn't have? Or have they made a genuine breakthrough in being able to get the kind of computing powers that you're saying they have from lesser materials?
So there are export regulations, in particular from the US, about top-end silicon processors going to China. So indeed, it looks like they've made some advances in the core architecture, what's called the transformer architecture, which is the neural network architecture that's underneath ChatGPT and Gemini and Claude and all of these large language models. And it looks like they've been able to optimize that architecture. So one of the key ideas, for example, is an idea called a mixture of experts approach. And the idea that instead of having one big, very, very clever neural network, you break it down into a bunch of smaller networks, which is much more efficient. Now, this is not a new idea. It's been around for a while, but it seems like they might have made it work. And that's quite an interesting development.
What about the quality and integrity of what it generates? Because there was concern expressed in a number of different quarters that when you ask it certain questions about certain things that China has sensitivities about, it doesn't answer the question.
Yeah. So first thing to say is we're going to need time to evaluate the model. I think teams all over the world are busy doing that. But at first blush, it does indeed look like this is a model which is in the same territory as the other GPT class models. Around the censorship issue, I think it's pretty well documented now that it appears that the model is censored in terms of some of the answers it gives. My advice to anybody using any large language model, wherever it comes from, is do not tell that model anything that you're not comfortable with your neighbors knowing or the world knowing about, because you don't know really where that data is going to end up. Don't tell it about your relationship problems or complain about your boss or anything like that, because really the text that you give, you just don't know where that's going to end up. Obviously, in this case, there are additional sensitivities because the model comes from China, and so that advice, I think, is particularly relevant there.
Yeah, if you look at I had a look at the terms and conditions, and it says the data are held on secure servers in China. And that is how you interpret that, isn't it? But are they basically creating a giant earpiece for the Chinese government with this? Because any industry in China has board representation from the government. It has to. And therefore, anything within that company potentially can be accessed by the government. The government can just request it. So are they basically, by getting people all over the world onto this and then feeding it all kinds of things they might not realise they need to be as careful as you're advocating for, it could be hoovering up all kinds of interesting things and reinforcing its knowledge about all of us.
Indeed, and I do think that's something that I think people need to be mindful of. That's something I think that governments have very quickly woken up to. Well, I mean, the advice I think is very, very clear. I do not tell any large language model anything sensitive, private, that you wouldn't want publicly known. Just don't.
Have you downloaded DeepSeek? Would you use it?
No and no. We would use it for experiments, I think, with caution. We would evaluate it. I wouldn't use it on my desktop machine.
You heard it from the man himself, AI specialist at Oxford University, Mike Waldridge there.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound. Perfect music for audio and video productions.
This is the Naked Scientists podcast with me, Chris Smith. Still to come, the hazards that the plant trade poses to our native species. Before that, though, the UK government has announced that it's going to dispose of over 140 tonnes of radioactive plutonium. This is currently being stored at a secure facility at Sellafield in the north of England. The UK has the world's largest stockpile of this hazardous material. So why have we got all of this stuff? Where can it go? And how can we safeguard it for the 1,000,000+ years it's going to take to cool down? Here's Claire Corkill, who's Professor of Mineralogy and Radioactive Waste Management at the University of Bristol.
Plutonium is generated from the reprocessing of spent nuclear fuel. So that's the fuel that's been in a nuclear reactor that we've finished using. Spent fuel recycling has generated us a large stockpile, 140 tonnes of civil plutonium.
And where is it at the moment?
It's currently being stored at the Sellafield site in northwest England in Cumbria in what you can think of as very large, secure, specially designed warehouses that are armed by guard police because this material has security implications. And it also needs to be actively cooled because it's constantly undergoing radioactive decay, which is generating quite a lot of heat. So we need to make sure that it's maintained in an inert and cool atmosphere.
Is there nothing we can do with it? Because the radioactive material, that's what goes into a nuclear reactor in the first place, in some respects. So is there no nuclear process that could consume this?
It could be useful for several different things. In France, for example, they use recycled plutonium to make new nuclear fuel. And to do that, they mix it with the recycled uranium that has the right isotopics. We call that a mixed oxide fuel. It's a mix of uranium and plutonium dioxide, MOX fuel. There are futuristic designs of nuclear reactor that could use plutonium as a fuel. And there are also other applications like space batteries, for example. It's a very long-lived radionuclide, which means you can use it to power satellites and rovers on Mars and so on. But that would only use a very small amount of the stockpile that we have.
Can we not just put it into nuclear reactors where the ferocious conditions in there would degrade the plutonium into other things so that we would turn something that isn't currently useful into something that might be, or something that's actually easier to deal with? Or is it easier to deal with just as plutonium?
You could use it as a fuel. There's a specific type of futuristic reactor conceived of quite a long time ago, and we had an experimental one of these in the UK at Dounreay called a fast breeder reactor, and that would actually use the plutonium as fuel, and it would consume some of that plutonium. The problem is with that type of fuel burning is that you end up generating other radionuclides that are quite hazardous. For example, americium is a very strong gamma emitter, and that makes it very hazardous for people to come close to that material. So there's a limit, is what I'm saying, to how many times you can use and recycle it. And ultimately, it will always have to be disposed of one way or another.
So what's the solution instead then that's being proposed that we do with this? It's quite a prodigious amount, 140 tonnes. You can't just put that any old place.
We do have the world's largest inventory of plutonium in the UK. It's not all of ours. Some of it belongs to international countries where we reprocessed, recycled their fuel, but we've kept the plutonium. What the government's policy has always been is to try and put it beyond reach. So the new plan is to do what we call immobilizing it, locking it up into a safe, durable form in a deep geological disposal facility, which is something that we're currently trying to find a site for in the UK.
What would be the nature of the storage, though? So you can't just put it underground, because presumably this is what, a powder, if it's an oxide of a metal, so it's presumably some kind of powder. So what can you actually do to make that safe so it's actually going to stay where you put it?
That's right, it is a powder. And so when we talk about immobilizing, what we mean is to take something that's potentially dispersible, like a powder, and turn it into a solid material. So what we plan to do is consolidate it, to densify it into a ceramic material. Most of you will think of ceramics as cups and plates and saucers. It's not quite that kind of ceramic. It's more like a rock. We can kind of think of it as an assemblage of minerals, quite a lot like a rock. And we can do that by adding powders of the plutonium with other chemicals together. We mix them, we bake them at a very high temperature, and that's when they become these very dense, durable, solid materials that then we could pack into canisters and transport down to the geological disposal facility, which is at a depth of around 500 metres to 1,000 metres below the Earth. And there it will be isolated from future populations until it's radioactively decayed to its stable isotopes.
I had heard from other scientists who work on this kind of thing that one problem with trying to sequester highly radioactive materials is that every time it undergoes radioactive decay, the nuclei sort of shoot backwards, almost like a gun recoiling, because they're firing out heavy things like alpha particles, and that damages the crystal structure, which makes the material fall apart in thousands of years rather than the millions of years you need it to stay safe for. Can you get round that?
You're absolutely right. The plutonium is undergoing radioactive decay to uranium, and then uranium also undergoes radioactive decay, and the alpha particles do damage the crystal structure. But what happens is the crystal structure becomes it becomes what we call metamixed. It's like a glass. It becomes amorphous. All of the atoms inside of the material become all jiggled up, but that doesn't affect its long-term durability. And we know that because we've examined natural minerals of the same composition that contain uranium. And these minerals, some of them are billions of years old. There's one particularly I'm studying right now, which is just over 1 billion years old. And it contains almost all of the original uranium that it had when it was formed 1 billion years ago. Despite the fact it's undergone a lot of radioactive decay, it's been squeezed in mountains, pushed out of volcanoes, it's been rained on, it's come into contact with high temperature underground water, it's maybe even been subject to glaciation. But during all of that time, the uranium that's inside that crystal structure, despite the fact it's been amorphized through radiation damage, all of that uranium is still inside the crystal structure. So we have a very good natural analogue that tells us that these kinds of materials will do a really good job at immobilizing, at locking away the plutonium over the long timescales required, which is on the order of 1 million years.
You do have to wonder, though, don't you, what the world's actually going to look like in 1 million years' time. That was Claire Corkhill. She's at the University of Bristol. Airlines estimate that there are over 1.5 million people airborne around the planet at any moment in time. And where people go, of course, they take their infections and other parasitic freeloaders too, and this is translating into a problem for disease spread and antibiotic resistance. But it's not just the movement of people that's a problem. We're also moving massive quantities of plants animals and other goods internationally, which are introducing infections as well as invasive species into brand new geographies, sometimes with massive consequences. Historically, it used to be just the odd spider or scorpion in a bunch of bananas, but a new study in bioscience suggests that even innocent-looking olive trees imported to spruce up the patio are home to stowaway snakes, lizards, spiders and insects. Will Tingle went to meet Silviu Petrovan at the David Attenborough Building at the University of Cambridge.
So olive trees are very interesting for a couple of reasons. One is that, as far as I can tell, actually there's this rather new fashion in relation to having olive trees, not just in the garden, but also associated, for instance, with outdoor spaces of restaurants. But the interesting thing is that actually that a sizable proportion of these olive trees are not the kind of stick ones, but rather very much actually the sort of quite hefty diameter trees. Very often actually trees that are decades old, which in effect means that these are trees that have been recycled from farmland. And the reason why people love these trees is because of their gnarly aspect, right? Almost any town and city in Britain will have some kind of public space that will have one of these kind of old growth gnarly olive trees. One look at it actually would give you an indication that, first of all, to transport it, you need a large root ball, which obviously presents lots of opportunities for things to be moved at the same time within that root ball. But then you have complicated bark, with sort of small crevices and little holes in between the branches. All of those basically are spaces where species can hitch a ride. And this now has been shown repeatedly as being a really major pathway for species introductions into Europe.
But if we know that then, if we know that, and we have known for some time, that these olive trees and their sort of gnarled pockets and crevices are great places for a lizard or a spider to hide, how is stuff still slipping through the gaps?
I think in the same way as with cut flowers, it's basically a numbers game. I think the customs officers are doing an extremely good job. However, if you think about the fact that these are very much actually involving large numbers, which means that ultimately not everything can be intercepted, how do you check a shipment of 500,000 roses, right? Chances are that actually you cannot verify everything down to the last flower. It's physically impossible, and therefore the chances are that something will slip through.
Are there any sort of main culprits that are coming through because of these olive trees?
Absolutely. So the one that we highlight in there is a lizard which people refer to as the Italian wall lizard, or also the Italian ruin lizard, Podarcis siculus. And that's a species that very often has been linked directly to the trade in olive trees. And the point that we're making is that in itself is not great. The fact that we're establishing populations of this species that is highly adaptable, it's actually surviving in a whole range of environments. But ultimately, the important point to make here is that the amphibians and reptiles are probably just the tip of the iceberg. And we got a lot of data on the interception of invertebrates. And there are, the sort of groups that very often actually represent the kind of main issues in relation, for instance, to one, becoming agricultural pests, two, potentially becoming established and then causing problems for the natural environment.
Are there smaller organisms that are hitching a lift that perhaps we don't even know about that could be causing even bigger problems?
Very often, a sort of main issue is the potential actually to introduce new diseases, new pathogens to a host that in effect actually would be completely naive. And a very good example, I think, in relation to this is to think back of the grey squirrel. The grey squirrel does create some competition with the red squirrel, with the native European species, but most importantly is the fact that it's able to transmit a virus that is extremely, extremely damaging for the red squirrels and very quickly actually eliminates them entirely.
Is there anything that can be done to even remotely stem the spread of these invasives?
Absolutely. So one of the relatively recent changes was the fact that virtually all plants now should not actually be potted in soil, which means that a huge area of contamination has actually been removed. It has been massively successful, but clearly there's more that could be done. as we have done in relation to potted soil, I think there are increasingly sort of targeted regulations that could achieve better outcomes, yes. One of the things that we also highlight is that while biosecurity in itself is a really important aspect of the environmental risk associated with this ornamental plant trade, it's by no means the only one. And we also highlight the fact that there are important considerations there in relation to water scarcity for the producing countries, the fact that some of these floriculture in effect actually competes in some cases with land being used for food production, but that ultimately it's also a really important economic activity for the producing countries and disproportionately for some groups such as, for instance, women working in rural environments. And therefore, we're absolutely not arguing for well-meaning but knee-jerk reactions such as, oh, we should ban this. This is definitely not the message that we want to put across, but rather that we need to have a careful discussion and see how we could achieve better outcomes for this trade.
I'm not going to look at the olive trees at the local restaurant in anything like the same way again. That was Will Tingle, who was in conversation with Cambridge University's Silviu Petrovan. Time now for our question of the week, and it's over to James Titko, who's trying to crack this one from Kevin.
As I understand it, petrol is a fraction of crude oil. Can crude oil be refined without producing petrol? If crude oil cannot be refined without producing petrol, then what will happen to all the petrol when we all drive electric cars?
Thanks, Kevin. You're absolutely correct that petrol, or gasoline, is a fraction of crude oil, obtained through a process called fractional distillation during refining. Crude oil is a complex mixture of hydrocarbons, and while refining processes can be optimized to prioritize certain products like diesel or jet fuel, completely avoiding petrol would be inefficient and require costly modifications. Your question is a pertinent one, Kevin, because the other fractions of crude oil produced during refining also include the types, as I mentioned earlier, which fuel planes and ships. We're going to need these types of fuel for a long time to come, as the kinds of batteries you'd need to power a Boeing 747 or transatlantic cargo ship for an average journey would be prohibitively heavy. So what will happen to petrol in a world full of electric road vehicles? Here to help us out is Professor Nilesh Shah, Director of the Centre for Process Systems Engineering at Imperial College London.
Thanks, James. Refineries could adapt in a number of ways. One idea is chemically processing petrol-range hydrocarbons to increase their molecular weight and make them compatible with aviation fuel. However, this would require significant investment in refinery modifications. Petrol and its lighter fractions could also be used for hydrogen production, which is another type of green energy, via reforming. This would need to add carbon capture and storage to reduce emissions, but this presents its own challenges. Or, petrol-range hydrocarbons, especially naphtha, could be diverted into the petrochemical industry for making plastics, synthetic fibres and chemicals. However, this would require investment in naphtha crackers and could lead to an oversupply of petrochemicals, making it less economically viable compared to cracking ethane or propane. This is perhaps the most promising option, but as you've heard, all of them have their drawbacks. With lower petrol demand, some refiners may shift towards bio-based or synthetic fuels to remain viable in a decarbonising world. We'll have to wait and see.
So, Kevin, crude oil refining cannot currently avoid producing petrol, but as demand falls, refiners would need to adapt through a mix of diversification strategies. Long term, the refining industry may shrink or evolve with different, greener feedstocks. Thanks to Professor Nilesh Shah of Imperial College London for helping us with the answer. Join us next time on Question of the Week when we're answering this one from Bill.
I'm sending this message all the way from Ballarat in Australia. I listen to bone conduction earphones without earplugs in preference to conventional headphones or earbuds. At times, I need to raise the volume to maximum and receive warnings via my smartphone. Neither environmental noise or speaker volume seem excessive or cause discomfort. My question is, do bone induction headphones without earplugs pose the same risk to hearing loss as conventional headphones or speakers? Thank you.
Thank you, Bill. And if you can help us out, why not drop us a line to chris@thenakedscientist.com with any answers or speculation. You can, of course, use that address to send us your new questions you'd like us to consider if there's something that you've been pondering on. It's chris@thenakedscientist.com. Also, you can go to our forum, nakedscientist.com/forum. There is a question of the week board there where we're discussing these and other quandaries. Before we go, do let me remind you, please, that you have been very, very kind to support this programme with your donations. It really helps, and I am writing to each and every one of you who send us a new donation every week. Some of you are even signing up to give to the programme regularly. This is a huge help. It does genuinely help to keep the programme on the road, and we are really, really grateful. Thank you again. If you appreciate what we do for you here and would like to show your support, please go to nakedscientist.com/donate. And we will be very, very grateful. That's all we have time for in this episode. Do join us on Tuesday, though, when we're going to be asking whether we can grow a building. Yes, you did hear that correctly. And actually, I was really very surprised when I made this show about what's going on. Join us on Tuesday to find out why. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith. Thank you for listening. And until next time, goodbye.